This is a short lecture on some simple alternatives to categorical accuracy for measuring success in binary classification. In a binary classification task, if we are solving it with a neural network, we will typically have two output nodes. And so all of our target vectors will either be 1, 0 or 0, 1. When our network produces a two-vector of outputs and we decode that to a category label, there are four possible outcomes. We could have a target of 1, 0, meaning that the data point belongs to the first category, and if our decoded output agrees, we call that a true positive. Whereas if the label should have been the first category and we labeled it the second category, then that's a false negative, because we thought that it was the negative category, but we were wrong and it should have been the positive category. For a label of 0, 1, we can again get it either right, which is a true negative, or wrong, which would be a false positive. I won't use the terms type 1 and type 2 error, but you may have heard them before, and they correspond to false positives and false negatives. Statistics has a lot of labels for the different possible rates that could occur between false negatives, false positives, true negatives, and true positives. In this figure from Wikipedia, the rectangle represents all possible inputs, and the points represent the inputs that are actually in our data set. The vertical line represents a correct decision boundary, separating the positive examples on the left from the negative examples on the right. And the ellipse represents a decision boundary of a model, where inside the ellipse are the things that the model labels as positive, and outside the ellipse are the things that the model labels as negative. And so we could measure, for example, the fraction of data points that are model labeled as positive that should have been labeled positive under the true labeling. This would give us the precision of our model. We could also measure the fraction of things that should have been labeled as the first category that we actually labeled as the first category. So this would be the number of things in the left half of the ellipse out of the number of data points with the positive label. And this is known as the sensitivity or recall of the model. And we could also measure the fraction of things that should have been labeled as the second or negative category that the model actually labels as the second or negative category. That's the true negatives divided by all of the things that should have been labeled negative, and this is known as the specificity. Comparing these to the accuracy metric that we've used so far, accuracy is the fraction of things that we gave the correct label to. So it is the things that our model gave the correct positive label plus the things that our model gave the correct negative label out of the total number of data points. So why are we concerning ourselves with metrics other than accuracy? Well, there are a few cases where accuracy isn't really what we care about. One case is when false positives and false negatives have very different importance for the model. This might be the case in medical diagnosis. And accuracy is also heavily affected by the fraction of positive and negative labels in the data set. If we have a data set where 95% of our data are positive labels, then we could just guess that everything belongs to the first category and get 95% accuracy. And so some of these other metrics or ways of weighting between them can help us focus on how well our model does, specifically on the positive or the negative categories. It's common for machine learning models to exhibit a trade-off between precision and recall. If we imagine that we are choosing among these different ellipses, where the size of the ellipse is a parameter of our model that we are allowed to play with, we could improve our precision by shrinking the ellipse where we predict label 1. With a small enough ellipse, we can get only positive examples in our positive label predictions, but that sacrifices our ability to capture most of the positive examples in the data set. On the other hand, we could get great recall by increasing the size, where with a big enough ellipse, we could capture all of the data points that should have the positive label, but that would be at the cost of labeling lots of things that should have been negative also as positive. There's also often a trade-off between sensitivity and specificity of the model. Sensitivity is the same thing as recall, and so in this example we could increase the size of the ellipse to increase the sensitivity. And while specificity is different from precision, it turns out that in this case we can also improve our specificity by shrinking the size of our ellipse, ensuring that out of the things that should be labeled negative, we do in fact label them all as negative by making the region where we label positive sufficiently small. These ellipses may seem like a contrived example, but these trade-offs between precision and recall, or between sensitivity and specificity, apply to a wide range of machine learning models. And so it's common to think about, for a particular model, how does that model trade off between sensitivity and specificity? A common way to visualize this is with a receiver operating characteristic curve. The ROC curve plots false positive rate against true positive rate. So if our model were to predict that everything belonged in the negative category, then it would have a 0% false positive rate, but also a 0% true positive rate. On the other hand, if our model predicted that everything were in the positive class, then it would capture 100% of the positive examples, but also give false positives on 100% of the negative examples. So these points at either end of the 45-degree line are extremes of the possibilities for how we could make predictions. And so if we were to guess independently at random between labeling things positive and labeling things negative, then we would move along this 45-degree line, where the probability with which we said positive would determine where along this line we end up. On the other hand, a perfect classifier would get true positives 100% of the time and false positives 0% of the time, and so would end in this corner. And so that means that we prefer machine learning models that are closer to this top left corner of the ROC plot. But if we think about training the same model with different hyperparameters, we might find ourselves at different points in this trade-off between false positive and true positive rates. And so if we were to connect up the points that we can get with a particular type of model, then we get an ROC curve for that class of model. And so for different classes of models, we will have different curves, and in general, ones that come closer to the perfect classifier curve are better. But even within a given class of models, we may, depending on the relative importance of false positives and false negatives for the problem that we are solving, we might choose different points along that model class's ROC curve as preferable for the problem that we want to apply the model to. So in working on your project this week, you should think about the trade-offs among your different models between false positives and false negatives, rather than just measuring the overall accuracy of the model.